This is the last lesson of this unit. In this lesson, I'm going to teach you how to make the last type of salt, and also we're going to discuss some of the applications of neutralization reaction. So in the previous videos, we have learned to make soluble salt except Group 1 metal salt and also ammonium salt. And we also learned to make insoluble salt. Okay, and in this lesson, we're going to deal with very special cases, those salts including Group 1 metals and also ammonium ion. Okay, so for those salts that including sodium, potassium ion and ammonium ion, they are also soluble salt. But what makes them so special? Why we need to take it out to discuss it separately? If we use the previous method to make this kind of salt, what would happen? Okay, so if we use the previous idea to make the salt, okay, we may suggest some of the method which listed here, okay, 1 to 4. Let's go through these reactions together. Are they practical method for making sodium chloride, which is a soluble salt? Okay, so first of all, the student suggested to put sodium metal into hydrochloric acid, so it will produce sodium chloride plus hydrogen gas. Would this reaction be okay? Remember, sodium metal is a pretty reactive metal. Okay, so we need to be very careful when we drop sodium into water because it's gonna have vigorous reaction with water. And remember, we suggest never put sodium metals in any acid because it's gonna cause explosive reaction. Okay, so we will not use this method to make sodium chloride, not practical. How about the second one? The second reaction is suggested to use sodium oxide with hydrochloric acid to make sodium chloride plus water. Okay, so first of all, is this reaction going to take place? The answer is yes. And then let's consider, can we separate sodium chloride easily from the side product and also the unreacted product? Okay, so for this one, the side product is water, so water quite easily removed from the mixture, we just evaporate it. However, the two unreacted reactants are sodium oxide that can be dissolved in water and also hydrochloric acid that's also dissolved in water. So how can we separate sodium chloride from these two unreacted reactants? Can we do that easily? The answer is no, so again this method not okay. Next one, the student suggested to use sodium hydroxide to react with hydrochloric acid, so it's a neutralization reaction which will produce sodium chloride with water. Again, okay, the reaction is okay, but let's consider whether we can separate sodium chloride from the side products and unreacted reactants. So side product we have is water, again quite easy to remove it, but we're going to face the same problem here. Sodium hydroxide, soluble, okay, it's an alkaline. Hydrochloric acid is an acid that dissolves in water, okay, aqueous solution. So in this mixture, we're going to have the unreacted sodium hydroxide and unreacted hydrochloric acid, one of them, okay, and also we're going to have some of the sodium chloride as a product that also dissolve in the mixture. So how can we separate it from the previous two? Again, not easy to do, so I would say that's not okay. How about the last one? Last one, the student suggests to use sodium carbonate to react with hydrochloric acid. This time, the product would be sodium chloride plus carbon dioxide plus water. So carbon dioxide is a gas, so it will escape from the system readily, so no need to worry about that. And then water, again, we can evaporate the water, excess water. And then we need to consider the same problem again. How do we separate sodium chloride in the mixture with the unreacted either sodium carbonate or hydrochloric acid? Okay, all of them are soluble compound that's colorless, and we cannot easily separate them. Okay, so again, I would say this method is not practical. Okay, remember on the previous page we discussed to prepare a soluble salt we need to use a solution and a solid in excess as reactant. So the solid, we put it in excess just to make sure that all the solution has been used to make the product we want. And then we can filter the solid to remove the unreacted excess solid. So the only thing left in the mixture is just the product we want. However, for the method that we suggested here, both the reactant are solutions and also the product are solutions. So we cannot separate them. Okay, so the answer is no. We cannot separate sodium chloride from the reaction mixture easily. So how can we prepare those salts contains sodium, potassium, and ammonium? How can we do that? Because we can't find a solid, okay, that's in excess. So here, the only approach is to make the salt, that is to mix a reaction in precise amount. So we will have nothing left for the reactants. Okay, we will use just amount of reactants to make the salt. So no unreacted reactants left in the mixture. So we don't need to worry about separated from the reactant mixture. Okay. So by doing this, to make it the precise amount, we're going to use this setup. Okay, and this setup is very important. If you are taking chemistry, you must learn all the apparatus shown on this setup, and also it's some very important reactions in chemistry. Okay, before we discuss the details of the setup, let's summarize the rules that to make those soluble salt containing sodium ion, potassium ion, and ammonium ion. Okay, so by preparing the salt contains these three kinds of ions, we're going to use an acid that will provide chloride ion, sulfate ion, and nitrate ion. Okay, so which one are we going to choose really depends on the target salt anion. Okay, and then we're going to use it to react with sodium hydroxide, potassium hydroxide, or ammonia, or we can use a salt like sodium carbonate, potassium carbonate, or ammonium carbonate. Okay, remember all the substances that we suggest here, they are soluble compound. Okay, so after the reaction, after the salt or the base react with the acid, we're going to have a water-soluble salt that contains the sodium, potassium, and ammonium ion in it, and that's our target salt. Now let's go through one examples together. You can refer to this video for the real experiment. So what are we going to do? First, we are going to work out what is a precise amount we need for this reaction. Okay, so from step 1 to 3, we're going to work out the precise amount. So here I want to introduce some of the apparatus that we are going to use in this setup. Okay, first we're going to use this kind of tube. It's called a pipette, or sometimes you can also hear others call it pipette. Okay, both are accepted. Okay, so what's the use of a pipette? So you can see a line, graduation line we call this. Okay, so by filling the liquid up to this line, we can precisely measure the volume of a liquid. Okay, remember we have compared if we just need to roughly measure, for example, 100 ml water, we can use a beaker. But if we want to measure it accurately, we may use a measuring cylinder. But a measuring cylinder, again, is not accurate enough. For doing this kind of experiment that requires precise amount, we're going to use one of these apparatus that can give you a more accurate measurement. So a pipette is needed to take the precise amount of the liquid. And then, how can we suck the solution into the pipette? Of course, we're not going to use our mouth to suck the liquid, right? So what we are going to use is called a pipette filler. So there are various kinds of pipette filler. It can be just a bulb that you suck it up, or you can see a bulb like this. You got some valves that can either draw the air or release air. Okay, you also got this kind of setup, but personally, I don't prefer this one, but I will let you to try different types and choose the one that you prefer. And then you're gonna see a long tube that's called a burette. Okay, so for burette, again, it's for putting liquid in it and adding liquids precisely. Okay, and you can see a valve here. So you can slowly turn it. So instead of getting the liquid going down steadily, okay, like the tap water going quickly into a beaker or a conical flask, you can actually slightly open the valve here, so it will add the solution drop by drop. Okay, so it can slow down the reaction and help you to add a precise amount of the liquid you want. Okay, so after learning the name of those apparatus, let's go back to the setup and take a look how we're gonna use them. Okay, so the first step we're going to do is to use a pipette to take a precise amount of sodium hydroxide solution and put them and transfer them into the conical flask. Okay, so that's one of the reactant we are going to use, which is sodium hydroxide. And then to make it just the precise amount, and when we need to know when the reaction stopped. Okay, when we get just amount of just the right amount of acid that can neutralize the sodium hydroxide. Remember, we have learned a lot of the indicators that changes color as when it changes from alkaline to acid or acid to alkaline. Okay, so in this reaction, we choose methyl orange. And how to choose the indicator is also an important task in this kind of experiment, and we're going to discuss in later units. Okay, so after adding the indicator, we're going to put the conical flask that contains the sodium hydroxide, the known amount of sodium hydroxide with a methyl orange, below the burette. And we are going to fill in the burette with the other reactants that we are going to use. So here we're going to use dilute sulfuric acid. Okay, so by using a burette, we can slowly add dilute sulfuric acid drop by drop to the solution in with the sodium hydroxide. Okay, so once we see a color change, that means all the sodium hydroxide solution has been used up. Okay, that means we have just added enough sulfuric acid to neutralize the sodium hydroxide. And then we're gonna stop the reaction and we take a reading and find out how much sulfuric acid we have used. Okay, but here, because the first time we have added the indicator in it, methyl orange, so that can be considered as a side product in the reaction. if we want to obtain the pure sodium sulfate crystal, we don't want any methyl orange in it. So we're going to repeat the experiment, but this time we are not going to add any methyl orange to the mixture in the conical flask. Okay, so it's not a mixture, it's just a sodium hydroxide solution now. Okay, and we're gonna add the same amount of sulfuric acid from the burette. Okay, so the sulfuric acid would just neutralize the sodium hydroxide solution, and there should be no unreacted reactants in the conical flask. Okay, so only left with water and the target salt, which is sodium sulfate. Now we just need to evaporate the excess water in the sodium sulfate, okay, and then we dry the crystals. Okay, so the last few steps just the same as the previous one we have mentioned when we make the soluble salt. Okay, so again, it might seem quite complicated. I highly suggest you to go and watch the video so that you can skip the part I explained it to you, or maybe refer it back to my explanation after you watch the video for several times. Now let's fill in the details of those steps that we did in the experiment. So first, we place a known volume of sodium hydroxide in a conical flask, and then we add some indicators. This indicator would give it a yellow color. And then we're going to place the dilute sulfuric acid into a burette, which is the other reactant, and then we're going to run it once and find out the precise amount of acid we need to neutralize the sodium hydroxide. And this process, we have a name for it, it's called titration. Okay, after we work out the precise amount of the two reactants we want, then we need to repeat the experiment, okay, without adding the methyl orange, so it won't contaminate our crystals. And then we're gonna heat the solution to concentrate it, and also to let it to cool down to make the crystal, and finally we dry the crystals to obtain the pure sodium sulfate crystal. Okay, so we have finished the last part of making salts. Now let's go through the checkpoint questions together. Please pause the video here, attempt the 3 questions on your notes, page 17, and then listen for explanation. Okay, question 1. Which of the following methods is best for preparing sodium nitrate? Okay, sodium nitrate, it contains sodium ion, so we need to choose a third method by using just right amount of an acid, contains the target anion, and also the other one should be either an alkaline that contains the sodium ion or a salt that contains sodium ion. So take a look. Okay, so for A, it suggests to add sodium sulfate to nitric acid. So it's not the suggested reactants that we suggested on your notes, but let's work out whether these will give us a reaction that produces sodium nitrate. Okay, so if we write it out, we have sodium sulfate to react with nitric acid. Okay, so both of them are soluble, so they contain mobile ion, and if a double displacement reaction can take place, okay, only if, let's assume what's going to be the product. It will be sodium nitrate plus sulfuric acid. Okay, so take a look at the product. Okay, it produces a salt together with a sulfuric acid, and the salt is soluble. Okay, so it would not fulfill the 3 requirements. It needs to either produce a gas, water, or a precipitate. But here, it only produce a salt and an acid. So actually there won't be any reaction. Okay, so it's not the first one. How about B? Add sodium to nitric acid. Remember, sodium is very reactive. Do not add it directly to an acid. C. Add sodium hydroxide solution to nitric acid. So this reaction is a reaction between a base and an acid, and it will provide the target salt plus water. So that's the correct answer. Take a look at the last one. Add sodium to zinc nitrate solution. So let's work out what's going to happen if we put sodium into zinc nitrate solution. So first of all, zinc is reactive than sodium is more reactive than zinc. So maybe some of you expect a displacement reaction to take place. However, remember, zinc nitrate is in solution, so it's going to have water. So the sodium will actually have a reaction with water as well. So it will not give you a pure product that we want. Okay, so again, it's not a practical method to make sodium nitrate. How about the second question? Which of the following equations represent a practical way of preparing the salt underlined? So let's take a look. The first one, magnesium sulfate. So magnesium sulfate is a soluble salt. Okay, so for soluble salts, we want an acid to react with a solid in excess. Okay, so here we have the solid in excess. Magnesium hydroxide is a solid. However, this time we do not have an acid. If we do not have an acid, then we are going to get some side product that's hard to be removed. Okay, so both of them are soluble, so they're going to stay in the mixture and we cannot easily separate them. So A is not practical. How about B? Okay, if we have ammonia to react with nitric acid, then we can produce ammonium nitrate. Okay, so this is one of the methods we suggested to make the salt that contains ammonium ion. So yes, and let's also go through C and D to see what's wrong with those two methods. And for C, it suggests to make copper sulfate by adding copper to sulfuric acid. Remember, copper will not directly react with an acid under room temperature. Okay, so again, this is not practical. And then the last one, we will have silver chloride to react with sodium nitrate to produce sodium chloride with silver nitrate. Okay, so the target salt is sodium chloride, which is a salt contains sodium ion. So we should expect to use an acid to react with a base that contains sodium, or a salt that contains carbonate salt that contains sodium. But here, it used silver chloride, which is an insoluble salt, to react with sodium nitrate. So because silver chloride is insoluble, so it will not contain any mobile ions. And also, if we look at the product, there's no gas or water or precipitate that's formed, so this reaction would not take place. So put a cross for that. And the last one, which of the following salt is best prepared by titration method? Okay, so only group 1 metal salt, sodium, the salt contains sodium, potassium, and ammonium ion that need to be prepared by titration. All the soluble salt can be easily prepared by adding excess solid and filter it. So no need to use a titration, and titration is not practical for those ions. So let's find out. So copper 2 chloride does not contain sodium, potassium, or ammonia. Again, B and C is not with sodium, potassium, or ammonium. Okay, so the correct answer should be D, potassium chloride. And if you have interest, you can suggest a correct way to make this kind of salt just to test your understanding for this unit. Here is a summary of what we have learned in this unit. So in order to work out the best method to prepare the target salt, we can use this flowchart to help us. So first, you need to ask yourself the question, is the salt that you want to make a soluble salt or not? Okay, if it's a insoluble salt, okay, so it says no, then we can use precipitation reaction or double displacement reaction. Okay, by using two solutions mixing together and produce a precipitate, and then we can filter the precipitate to dry it to get the pure target salt we want. Okay, please refer to your notes page 11 to 13 for more information. If it's a soluble salt, then we would follow this road, and then we need to further ask ourselves another question. Is it a sodium, potassium, or ammonium salt? Okay, if no, then we would choose an easy method. We just use an acid that contains the target anion to react with a metal, or an insoluble base that contains the target cation, or an insoluble carbonate that contains the target cation. And remember, we need to put the solid in excess to make sure we have used up all the acid in this mixture. Okay, so we can easily filter away those unreacted excess solid, and then we can dry our target salt. Okay, and the last type, if it's a sodium, potassium, or ammonium salt, then we need to use the titration method to prepare it. So we can again use acid that contains the target anion, and then we need an alkaline that contains the target cation, or a soluble carbonate that contains the target cation. Okay, so more information you can refer back to the notes. In the last part of this video, I'm going to discuss some of the applications for neutralization reaction. So the first one is to use neutralization to balance the pH in the soil. If the soil is too acidic due to the acid rain, then it will not produce, or the plants cannot grow properly. Okay, so the farmers need to neutralize the acidic soil by adding quicklime. Do you remember quicklime? So quicklime got the formula CaO, calcium oxide. Okay, so by adding quicklime, so it will react with the excess hydrogen ion in the soil. So it will undergo this reaction and produce calcium ion plus water. Okay, so that's one of the application. Also, it is used to make some of the important fertilizer, for example, ammonium nitrate and ammonium sulfate. Okay, so the first one, how do we make ammonium nitrate? Is to make use of the nitric acid and then react with ammonia. So it would produce ammonium nitrate for us. Okay, and also we have ammonium sulfate. That's also an important fertilizer, which is made of using sulfuric acid together with ammonia solution. It would give us ammonium sulfate. Remember to balance the equation. Okay, and the next application, we have mentioned this before. Okay, we know some of the bases that are used as antacid tablets. So the examples include magnesium hydroxide and aluminium hydroxide. So they're gonna react with the excess hydrochloric acid in your stomach. So the reaction we can write out between magnesium hydroxide and hydrochloric acid to make magnesium chloride with water. And also we got a reaction between aluminium hydroxide and hydrochloric acid. So it would produce salt, aluminium chloride with water. Okay, and also remember to balance this one. And the last application we're going to discuss is a lot of the time on industry, we're going to produce a large amount. We are going to do a lot of chemical reactions in a larger scale. Okay, so some of the waste may contain a lot of acidic product or acidic compounds in it, and if we just directly let those acidic waste go into the ocean or even go into the river, it's gonna cause problem. Okay, it's gonna kill those living things in the river or the ocean. So we must balance the pH before we discuss those waste. So how do we do it? We often use calcium hydroxide to neutralize the acidic waste. So it will undergo this reaction. And produce calcium sulfate. Okay, remember you need to balance it. And then write the state symbol. Okay, so here you can see the product is calcium sulfate, so we can easily filter it or let it to settle down so that we do not get the waste into the environment easily. And also, I want to leave a question with you. Why here we use calcium hydroxide, not sodium hydroxide, to neutralize those excess acid? Okay, please leave your answer on Google Classroom or just text me if you want to know the answer. Okay, finally, let's go through the checkpoint questions. Again, pause the video now, complete the questions, and then listen for explanation. Question 1. Which of the following substance is commonly used to reduce soil acidity? Okay, so answer provided with ammonium sulfate, sodium chloride, magnesium nitrate, calcium oxide. So here we need to choose a base to balance the soil acidity. So the correct answer should be D. Next one. Which of the following chemicals is or are used to neutralize the excess acid in stomach? So the answer provided with magnesium hydroxide, calcium hydroxide, and sodium hydroxide. Okay, so on our notes, we suggest to use magnesium hydroxide and aluminium hydroxide. So is calcium hydroxide okay to neutralize the excess acid in our stomach? The answer is yes. And how about the last one, sodium hydroxide? Do we use sodium hydroxide to neutralize the excess acid in our stomach? The answer is no. And the reason for that is sodium hydroxide is a strong and corrosive alkaline. Okay, so we will not use it to neutralize the excess acid in our stomach because it may cause other problems. The last one, which of the following is not used to neutralize the acidic liquid waste from industries. Okay, sodium hydroxide, sodium carbonate, calcium carbonate, or calcium hydroxide. Okay, so here I have asked the questions a bit earlier. Okay, which one do you think we should not use it? The correct answer should be A. And the reason for that is, again, sodium hydroxide is a strong alkaline, and when it neutralizes with, for example, sulfuric acid, it would generate a great amount of heat. Okay, which if we do it on a large scale, it's gonna be quite dangerous. Okay, so that's the end of this unit. If you have any question, please contact me, and please also attempt the exercise for this unit.